Today we are going to talk about some of the conjugate forces that drive diffusion. So we've been focusing so far on chemical diffusion. So basically flux in response to a chemical gradient, a gradient in concentration. But there are lots of different kind of driving forces that can basically cause particles to move and cause diffusion to occur. Some of them are kind of described here. So we've been dealing with, again, a gradient in concentrations or equivalently chemical potential. You can also get diffusion based on basically charges, right? So we can't go through all the other different so many examples of charged species, but you can kind of look at the example of a lithium-ion battery. So we have basically two different kind of diffusive contributions here. Let's look at kind of this example here. So if I have an electric field here, and it's pointing in this direction. So if I have charged species, so you can kind of imagine this is like Na plus and Cl minus. So if I have an electric field pointing in this direction, hopefully from basically physics and E&M, I'm going to get a flux of, there's going to be a driving force based on this potential, this electric field potential. The flux of our positive kind of ions here are going to move in this direction, and the negative ions are going to move in the opposite direction. Now, that would kind of imply that eventually all the pluses are going to be on this side and all the negatives are going to be on this side. But then I'd have this kind of opposite gradient of, now I have high concentration here. Shouldn't my gradient in concentration of these like Na plus ions, for example, shouldn't they move to kind of go in the opposite direction of the electric field? Well, this is kind of the critical kind of idea, because in real life scenarios, there's often going to be multiple conjugate forces that are kind of driving the diffusive behavior. So there's going to be two diffusive contributions, one that's chemical in nature, one that's electrical in nature. So you can tune and actually change the magnitude of each of these kind of contributions. So this chemical gradient versus the potential gradient from the electrical field. And you could tune it so that eventually the flux, the magnitude of this Qj here, we could change the magnitude of this potential and basically have it where the flux is zero. Or you can also, again, achieve uphill diffusion. Again, if this contribution is really, really, really large, it doesn't matter if we get this kind of chemical potential built up, because this is dominating the behavior. So you can get this phenomenon called uphill diffusion. So when the electrical component is larger, we actually push all those positive ions and we kind of create kind of that scenario that's occurring here. You could also have a temperature gradient. So temperature, chemical gradient at the same time. And typically, atoms are going to move towards a higher temperature. So that's kind of the nature of most atoms. Again, there's always exceptions to the rules, but higher thermal energy, so the flux of atoms, they'll tend to kind of accumulate on this side. And again, you'll get accumulation of atoms here. So why wouldn't they move opposite in that direction? So again, it's this competition of which magnitude is larger, this or this. That's the competition that we're dealing with here. You could also get curvature, basically a conjugate force. So we typically atoms, or we don't like curved interfaces. We want to move towards a flat interface. So often we'll move from basically high curvature. So actually this is in the opposite direction if you kind of flip it. So high curvature here to low curvature here, because this is here we're positive curvature. This is going to be, or if we're kind of sitting here, we're going to go from high curvature to low curvature. So the atoms are going to kind of move down and basically evolve into a flat interface. So from high curvature to low curvature, positive curvature to negative curvature. So that's where we're kind of moving in that direction. And you could also have a stress-driven gradient as well. So we talked about edge dislocations, right? Where here at this point we have like all these packed atoms, and then here there's kind of like open space. So again, for stress gradient, we want to move towards areas from high compression to tension here. Let's go back. Let's look at the stress-driven gradient. So we're going to move from those compressive, near edge dislocation, we'll move from these compressive regions towards these tensile regions. So one of the cool things, and it's called this Cottrell atmosphere, and you can kind of look this up. You can kind of see that, again, you'll have these two different, a gradient in chemical and a gradient in kind of the stress, behavior as well. Let's go back to our kind of slide here. So here you can see relating to stress or hydrostatic stress gradients right here. So you can imagine a scenario that can occur where atoms, and actually this happens a lot in terms of steel. So in steel I have iron and carbon. So my little carbon atoms, carbon here, let's say that they're initially, here in their interstitial sites. But if they're near an energy dislocation, they don't want to be in this compressive region. They'll instead want to kind of diffuse and move, and they'll start to accumulate here. And when these carbon atoms accumulate here, they actually form this Cottrell atmosphere, where then they pin this dislocation from moving, and you get these kind of really unique behaviors in your stress, strain curve, where you get this another uptick. You could kind of read through that on your own time, but very interesting phenomenon. Again, you could start to get a buildup of these Cottrell atmospheres, but then again, it's always this competition, right, between this gradient and this gradient. So which is larger? So eventually, the concentration gradient will be large enough where it may overcome this, but it pins those dislocations. So next time we are going to get into basically fixed second law and determine when are we going to, or how can we describe. So far we've been looking at where's the direction of flux, but we know that diffusion is a function of time and position x. So we are going to get into fixed second law next time. Thanks. I'll see you in the next video.